Hi, and welcome to Pennichuck Waterworks Treatment Plant. My name is Chris County. I'm the Director of Water Supply and Community Systems for Pennichuck. And today I'm going to take you through a tour of the water treatment facility. We'll be touring some of the older buildings like I'm showing you now. This is the Snow Station Pump Station, originally erected in 1893. Was pretty much the primary pump station up until 1980. We'll talk a little bit about that in a minute. This is the supply pond that was the supply for the city of Nashua until the treatment plant was built. It's kind of interesting in that there are three ponds above this pond, upstream of this pond, Harris, Bowers, and Holt, that hold about a half a billion gallons of water. And for the most part, that water was diverted as it flowed through the brook system into three man-made bogs that are in the woods behind these trees in the woods there, and they would surcharge about 45 driven wells out in the woods that in essence surcharge the aquifer, the sand aquifer, that would provide treated water, if you will, to this supply pond. And up until the surface water treatment plant that was built in response to the Safe Drinking Water Act, in particular the requirement to treat to remove disinfectant byproduct precursors. This was the supply for the city of Nashua. We withdrew it from this at one of two locations. That's the Dean and Main building there. There's an original pump station that didn't have pumps, or had pumps originally, but it currently is used as a garage. And again, the Snow Station. Sorry for the quick pan. And we chlorinated, added some sequestrant for iron and manganese control, and that was about it. Pumped directly into the system. What you see here is the facility. There's the treatment plant that was built in 1980 originally, and then was upgraded in the middle 2000s, between 2003 and 2009. About $40 million of upgrades to basically replace all of the mechanicals, all the filters, all the actuation valves, and basically make it a brand new plant after it had not been able to really keep up with the current level of regulation that was we were facing. This is the Harris Pond, and this is where our primary intake is. You can see in that building there, that's where the intake is. That's a Manchester Street bridge that runs from Nashua to Merrimack. The Harris Pond is the second to the last pond in the chain of impoundments that make up the Pennichuck Brook Reservoir system. It has about 300 million gallons of water stored in the pond, and generally has been a good source of supply. We do supplement it in the summertime with water from the Merrimack River, and we'll see that in a little bit. Water is fed by gravity through the 72-inch penstock that used to feed the turbine in the Dean and Main building, and now is and the 42-inch line was connected to it to feed the treatment plant when the original plant was built in 1980. And so we benefit from the fact that we don't have to pump into the treatment facility from these ponds. It all flows by gravity. This is the Harris Dam, which is the second to the last dam in the series of dams that impound the Pennichuck Brook. This dam was built in the late 19th century, has been improved over time. Most recently, around 5 or 6 years ago, when we added these sluice gates and improved the spillway. This is the Dean and Main pump. It's on site of the water treatment facility. It's still not operational. Get my thumb out of here. But it is still retained as a historic landmark, if you will. Basically, you'd have to take down the building in order to get this pump out of here. Originally pumped about 7 million gallons of water a day. It is a positive displacement pump driven by a turbine, hydraulic turbine that's in the basement of the building. 16-foot diameter flywheel would have been connected to that turbine in the basement, and would have driven that shaft to drive those arms back and forth on each side. There's a gear drive inside that enclosure there, and then pumped these vessels, if you will, would be in alternating suction and discharge mode, and then discharge out to the city from there. This pump ran up until the 70s, and again, pumped about 7 million gallons of water a day. This is the Merrimack River Pump Station, where we withdraw raw water to feed into the treatment plant. Feeds directly into the treatment plant, up to 22 million gallons a day. There are 2 pumps currently in this station, 2 350 horsepower pumps. A 3rd pump will be added later on this year for redundancy. The intake is underwater, of course, about in the middle of the river there. It's a 48-inch steel line that runs out to 2 screens, relatively fine screens. Within that structure, there is an air burst system. Those are the lines that run to the air burst system, and so once a day that is charged with air and cleans the screens themselves to prevent any type of buildup. That was completed in 2019. The station was originally built in 1984 and was originally just for seasonal usage in the summertime when there are periods of high demand for irrigation and other things. It is a year-round source now. This is was a chlorine station prior to it being converted to a pump station that allows finished water to be pumped across the river via another line, 20-inch line that was installed in 2017, 2018 to the other side of the river in Litchfield, and connected to the Litchfield system, and eventually actually runs into the Hudson system as well. So this is the headworks of the treatment plant. Water flows by gravity from the Upper Harris Dam into the treatment plant here. We have about 6 feet of head difference between the elevation of the water, 6 or 7 feet, the elevation of water at the Harris Pond, and the inlet here. So we have enough driving head to get the process through without having to do any pumping through the process. We use ferric chloride as our primary coagulant, primarily because of its positive sludge characteristics, so that we can dispose of our residuals at the National Wastewater Plant. We also add a high molecular weight non-ionic polymer as a flocculant aid, and then we also are adding 50% caustic soda for alkalinity adjustment, pH adjustment in the inlet works. Water flows, again, by gravity, over these 2 weirs. The drip points that you see right there, that's where the polymer is being added. And from here, it dives beneath the building into 2 36-inch diameter lines and go to one of 2 upflow clarifiers, which we'll see in a second. Is one of 2 pulsator clarifiers. There is the center vacuum chamber with the blowers on top. Again, raising a column of water, in this case about 15 inches, and then releasing that, sending a pulse of energy through the distributor pipes in the bottom of the clarifier, in this case about 14 feet deep. And that's making that blanket a homogeneous blanket and puffing it up so the top layer of the residuals can flow into the concentrators, as the video showed. Clarified water collected on top. You can see also, barely, if you look closely there are what are called tube settlers just below the collector pipes. And basically those tube settlers are in place of the plate settlers that you saw on the YouTube video. They have the same angle, if you will, and they basically create a backstop to keep the blanket from coming up into the area where the clarified water is. Again, water collected in the collector pipes flows beneath our feet, or my feet, and then onto out into the filters. There are two clarifiers. Because it is an imperfect system, it's not 100% efficient, we will take the clarifiers down once a year for cleaning. Operators will get into the bottom of the chamber, will drain them, of course, and work the sludge that has accumulated on the bottom to the drains. And then we have two on-site lagoons that we send those residuals to, where they're allowed to go through a freeze-thaw cycle. We do that rather than send it to the city of Nashua's POTW, because we found that when we did, prior to the construction of those lagoons, that overwhelmed their process, and it was just too much coming at them at once. So those lagoons were built in 2003 to accommodate the annual clean out of these clarifiers. Here you see one of the SCADA screens for filter 5A, and it shows you the basic configuration of one of the 12 filters in the plant. Water flows into the filters from the clarifiers, and you see there we have about 4.5 feet, but it's actually closer to 5 feet of media. They're conventional filters with a nozzle underdrain system with about a 1'11" plenum space underneath, where the water flows into the effluent valve and into the contact chamber. Swinging around to the filters, you can see that there are 12. Not much to see, unfortunately. A lot of stuff going on underneath. The GAC is 8x20, was last replaced within the last 2 years. We normally will stagger the replacement of the filter media, whereby we do 4 beds. 6 months later, we'll do another 4 beds, and then 6 months after that, we'll do the remaining 4 beds. The last 4 beds were done in early 2020. We do that because we want to use the GAC and then try to stagger the cost. The cost is about $1.5 million for all 12 filter beds. $1.5 million is the last cost we had. We're using the filters. Originally, we were using the carbon for taste and odor, and also as kind of a backstop for any type of contamination event that would happen in the Pennichuck Brook system. We still are using it for that purpose, but with the implementation of the new PFAS regulations in the state of New Hampshire, as we were doing our monitoring, we discovered that the raw water at certain times of the year in the Pennichuck Brook system exceeds the PFOA MCL that was established of 12 parts per trillion. GAC and the amount of contact time that we have in these filters is effective in removal of PFOA, and we have found that this is the case, and it does a really good job. So we combine blending the Merrimack River, which has PFOA levels very much lower than the Brook system, and we blend that with the Brook system, and then final treat it, if you will, with the carbon media, and our finished water PFOA levels are well below that standard. Again, the staggering is done, and we monitor on a frequent basis the effluent of these two filters, because they have the oldest carbon, to make sure that we're not seeing breakthrough of these original filters, to give us an idea of when we need to plan for our next change out, so that we can change out these 4 filters and still have effective treatment in the remaining 8. We suspect, or expect, I should say, that our carbon media lifespan will be less is we expect that we'll see breakthrough of PFOA prior to when we would have normally seen a reduction in the iodine number of the carbon, which we also monitor. So we're thinking that we'll get at least 3 years of life out of the carbon media, and we're hoping for more. But again, by using the river, Merrimack River, and blending with the brook, we hope to constantly keep our raw water below that 12 part per trillion. Filters are backwashed based on head loss. They can be backwashed based on turbidity breakthrough or particle breakthrough, but generally we don't see those two conditions before we see the head loss build sufficiently so that you're no longer flowing water through the filter. So taking a walk downstairs, those filter bays and the clarifiers that we looked at upstairs were in essence on that second floor in that area behind that wall. There's the blowers for the backwash for the filters, 2 units. This pit is where the inlet control valves are, and so we're regulating the water flow through the plant by modulating those valves that are in that pit. Some raw water instrumentation. Some post-chemical addition instrumentation. And then walking into what we call the North Pipe Gallery. And so this is on the filter effluent side, if you will. We'll walk up to one of the filters and go through some of those valves there. Turbidity meters and particle counters. So here are the air scour inlet valve to filter, I think this is 6A. Again, some of the piping down below, some of the actuators. Basically, again, filter backwash starts with an air scour. There's a backwash valve beneath my feet that allows water in through that plenum space, backwashes the filters. Approximately 10,000 gallon a minute for the high rate wash. That gives us enough media expansion to get the kind of a targeted 20% expansion of the media so that we get proper cleaning. In the summertime, this time of year, we're getting about 36 hours of filter runtime. In the winter, we may get as much as 5 to 7 days of runtime through those filters. Again, 12 filters. Each filter is equipped with filter to waste. And so at the end of the filter wash cycle, as the filter is ripening, the effluent is allowed to flow into one of 2 tanks. We have 2 recycle backwash tanks holding about 500,000 gallons of water. And then that water is recycled back to the headworks of the plant. In the upgrades of the treatment plant that were started in 2003 and finished in 2009, we addressed a water quality concern that we had over the years of raw water manganese, in particular in certain times of the year at pond turnover, where we would get a large amount of dissolved manganese through the process, which we had no facilities to remove. And so designed into the plant was the ability to feed sodium permanganate at the headworks, add caustic at the headworks at the intake to raise the pH to 7.8 so that to optimize the oxidation of manganese in the raw water. And then we would add CO2 further downstream to then reduce the pH back down to our coagulation pH and add alkalinity while not consuming alkalinity, to pre-oxidize, if you will, the dissolved manganese, and then be able to remove it through our filters and through the process. Part of the upgrades also had us install aeration systems in the ponds. And what we found was that that aeration system allowed us to keep the ponds from stratifying, and therefore we haven't had to use this CO2 system along with the permanganate, which is a pretty pricey proposition, to remove that seasonal manganese, because the aeration system and the fact that we're keeping the ponds from stratifying has kept the raw water manganese at the level that we want to leave it at, that below 0.05 and typically 0.02 to 0.03. Continuing our walk through the pipe galleries, this is what we call the center pipe gallery. This is the waste side of the filters, if you will, and so when the filter goes into a backwash, water is collected from the top of the filters and then goes out this line out to the recycle tanks, filter recycle tanks. This is these are the blowdown valves for the sludge extraction. Again, 2 pulsators, 6 concentrator chambers. And so how this system works is the flow through the plant is metered, obviously, and the sludge blowdown frequency is set by flow through the plant. So currently at about once every 850,000 gallons of flow through the plant. These blowdown valves are actuated. It's a plug valve by gravity through the filters and the concentrators, so you have some driving head that forces the sludge that's concentrated in those, again, the concentrators, and then we dispose of that through this line, and it goes to the City of Nashville wastewater treatment plant, and they're good enough to take that for us at a cost of about $300,000 a year. But in the grand scheme of things, that's much less expensive than others pay for residuals handling. And so it's beneficial for us to continue that process in the use of ferric chloride, because otherwise we would have to construct some type of lagoons on site for residuals handling, and frankly we just don't have that space on site. These clarifiers are not 100% efficient in that some of the sludge does settle to the bottom of the concentrators, and so once a year we do drain them down, and the crew gets in there with hoses, squeegees, and cleans out the bottom of those clarifiers. Okay, taking a walk through the chemical feed hallway, if you will. Here are the ferric chloride day tanks. See? The chemical feed pumps, diaphragm pumps, bulk tanks. If you don't know it, ferric chloride is a pretty nasty chemical. It does stain very readily because of its iron content, and so we have occasional spills. Here's our polymer feed system. It's a dry feed system, an Ackerson dry feeder. We're feeding polymer at a rate of about 0.21 milligrams per liter, again as a flocculant aid. One of 2 bulk storage areas for sodium hydroxide. Again, we're using 50% sodium hydroxide, so these rooms are sealed rooms, if you will, in the winter time. The freezing point of 50% caustic is about 54 degrees Fahrenheit, and so we are certain to make sure these rooms are maintained above that level. We don't have to worry about it through the pipe chases because we're adding push water, and so we're reducing the concentration and therefore the freezing point. Again, diaphragm feed pumps going to 2 trains and then 1 in backup. Originally this room held lime silos, hydrated lime silos, that were the original means of adding and adjusting alkalinity at the headworks. The lime is inexpensive, but from a operating cost perspective and a consistency perspective, very troublesome to deal with, and so we got rid of the lime and went to sodium hydroxide. Here's the chlorine day room. We're using peristaltic pumps here, the hose pumps, if you will. They've been relatively trouble-free. We use the hose pumps here to eliminate gas binding, and it gives us a good consistent feed. We adjust the speed of the motor based on the flow, and then we can adjust that by selecting, by changing the trim percentage, if you will, or the ratio of the ratio to the actual influent flow or finished water flow, depending on where we're adding the chlorine. We can add chlorine at multiple points in the plant. Push water lines. We use sodium hypochlorite, so we're using bleach. We're very fortunate in that we have very low disinfection byproducts in the distribution system. Typically, below 60-40 consistently. So we're not in any there have been no problems with disinfection byproducts treatment. We achieve about 78 to 80% of a removal efficiency of TOC through the process, and the raw water is very low in disinfection byproduct precursors anyway. So we've been very fortunate in that regard. So we do use sodium hypochlorite as our primary disinfectant, and we leave the plant at about a 1 part residual free chlorine for disinfection in the distribution system. And that maintains a good 0.5 at least throughout all areas of the system. So back outside, this is the older of one of two backwash holding tanks. You can see that it's due for a clean out, and that's been planned. This one holds about 200,000 gallons. It's the original backwash holding tank prior to the addition of our ability to filter the waste. Here's the CO2. And then you can see the additional 300,000 gallon backwash holding tank. Again, that was added to facilitate filter to waste and give us a little, and also be able to adjust the rate of return into the headworks, allow a little bit more time for it to store, and recycle it back at a little slower pace if we need to, if we're having some water quality issues related to filter return, if you will. Outside of the building, all sorts of nice 70s architectural features. You can tell when the thing was designed. So the water from the filters collecting in the bottom drops into a contact chamber beneath this building. It's a 1 million gallon contact chamber, and flows through that contact chamber where we perform our primary disinfection. Walking from that process area now down into the finished water pump station. This was a new addition that was installed in 2007. Originally, the pumping facility to the distribution system was in the opposite end of the building where the air scour blowers were. The contact chamber in the upgrades was actually changed in that the direction of flow was reversed, so that the filters, rather than flowing originally east to west, they go west to east and then enter into the finished water pumping station, where we have an additional contact chamber, if you will. That's a 6.5 million gallon contact chamber that's on top of the hill. I'm going to walk through the pump room. Might be difficult to hear me over all the noise. Currently we're pumping at about a rate of about 23 million gallons a day. And what I'll show you is are the intermediate pumps that take water from that contact chamber beneath the old building and pump it to the 6.5 million gallon contact chamber. And then I'll explain to you in a bit why we do that. the intermediate pumps. These pumps run on variable frequency drives and basically maintain a constant level in the wet well that they're drawing from and pump up to what we call the Concord Street tank. Here are the finished water pumps. They're across the line, and they're pumping to our 5-field storage system. Parco actuators. So, here's a better overview of what you're seeing out there, and hopefully you can see this and I can describe it. Sometimes it's difficult to be clear, but on the top of your screen you'll see the 5 intermediate pumps. That blue tank, if you will, beneath them represents that clear well. The Concord Street tank is in the far upper right-hand corner, and that's showing the level of water in that tank. The reason we have so much finished water storage and so much contact chamber space, if you will, is because remember how we talked about the theory of operation of those clarifiers, and that your upflow velocity equals your settling velocity. And there are a number of things that can, well, a couple of things primarily that can really impact that. Number one is a change in temperature. We address that temperature change by adding the aerators in the raw water and destratifying the pond, and so we don't see that significant, and also went to a deeper intake so that we don't see a change in temperature, a 4 to 5 degree change in temperature that we would see in a hot summer day anymore. And then secondly, a rapid change in flow. In the old configuration of the plant, we would see some significant increases in demand during the course of the day that we would have to adjust to in our finished water pumping side. Because we needed to maintain CT in the existing contact chamber, we would also have to ramp up the influent flow quite rapidly to match that and to maintain CT for primary disinfection. That, of course, caused some disruption in the clarifier, caused the turbidity to overflow from the clarifier into the filters, shortened filter run times, and impacted our ability to treat properly. So what the 6.5 million gallon contact chamber now allows us to do is it gives us some redundancy in the contact chamber, number one, so that we can take the 1 million gallon contact chamber out of service for inspection and maintenance if need be. But it also allows us to adjust our effluent flow out to the distribution system to react to change in demand in the system without having to adjust our influent flow through the process. We, in essence, draft and fill that tank during the course of the day. So that's how that's been working since 2009. It's been very effective. We're very consistent in our flow rates through the process, and when we do make changes, they're very subtle and very slow, and so the clarifiers have time to react to that. One of 2 large generators on site. This is a 1250 kW generator. It's a diesel generator. Prior to the upgrades to the treatment plant, we did not have a generator sizable enough on site to run the high lift pumps that were pumping in the distribution system. Instead, we had a system whereby if we lost power and lost our ability to pump, the operator would run downstairs to the snow station building, start a natural gas engine, hopefully pick up prime on that centrifugal pump attached to it, and then start pumping back into the distribution system. All the while the process was still flowing by gravity through the plant, and oftentimes overflowing the clear well. And in the meantime, he would also have to be resetting all the chemical feed pumps, you name it. This system, obviously, that was something that we needed to address in our upgrades, and this is one of 2 larger generators now where this is to run the finished water pumps that we saw earlier, and then there's another generator on site to take care of the process, all the chemical feeding process. So in the event of a power outage, it's much smoother and less stressful on the operator and less likely to cause any disruption to the system. Finished water chemical feed facility. We're using sodium hydroxide, again at 50% strength, to adjust the finished water pH to about 7 to 7.4. And we can maintain that consistently throughout the distribution system. We're checking that at each bacteria sampling site. We're also adding tetrapotassium pyrophosphate as a sequestrant for the little manganese that we do have running through the system. And then we also are adding a zinc orthophosphate for corrosion protection as part of our corrosion protection plan.